Hello! Right, this is chapter 19, okay, quantum physics. So the best way to use this video, like I keep telling you, is to go through it with me. If you stop anything to read something in the book, do it. And also have a go at the questions. Big thing, practice, okay? And that includes, after you've done all this, doing exam type questions, okay? So be ready to go and to press pause. Okay, so if you want to read about page 208, a little bit about macroscopic models, which are models to do with the large world. Okay, that's okay. Have a little read of that now. Okay, but anyway, I shall start now looking at page 207. And basically the two ways you can look at things are either looking at them as particles, a solid lump, or as waves. Okay, and you know things like waves that transfer information. They can travel like a wave, like a water wave, unsurprisingly. Okay, so you can see there's lots of little models that you can talk about in terms of on page 207. Things like what types of physics, like the area, there's a model, and there's a macroscopic phenomena it describes. So something you can actually quantify quite easily by using a model. Okay, and in most terms, particles are quite easy to conceptualize. Waves maybe not as much. Okay, so waves are something like you might see on the sea. Going along, so page 207, and it goes on to there talking about different ways you can model phenomena again in waves on page 208. But the question is what model do you actually use? And both serve a purpose, both try to explain something, but sometimes it just does not really make much sense. But the question is could you actually consider light acting as a particle? And yes, you can. Okay, so the idea that perhaps gamma rays do actually have something that registers on a Geiger counter might mean that there's something photon-like about it. Okay, so photons are the idea. If you turn to page 209, okay, so photons are something that is a concept to do with a wave can act. Instead of just purely as a wave, there could be a particulate nature to it, and those little particles or quanta or corpuscles, as you see Newton called them, they are called photons. Okay, so the idea is that photons, and there's some equations on page 209 that you need to know, quite simply, that if you have got a photon and it's associated with a light with a certain frequency, which is a wave property, then you can say its energy is equal to h times f. Okay, h being the Planck constant. Okay, named after Max Planck. So there you go. So if you can look on through that, okay, you can actually link two equations. Here we go. All right. So if you have a little look there, that's the Planck equation, E equals hf. And if you look down again, because of the idea that E is directly proportional to frequency, higher energy. Quite simple. And again, because you can substitute frequency using the wave equation as speed divided by wavelength, you can also replace f in that equation to give you E equals hc of a lambda, which is again two equations you will need to use. Okay, so if you want to have a little practice of those questions right now, okay, there are some questions on page 209. Have a go at those now. Press pause. Hello. Okay, right. So going on to that, okay, it makes sense, okay, if you're talking about small values of energy, because energy in terms of photons for frequencies around visible light and around all of wavelengths, to be honest, okay, those frequencies give you very, very, very small amounts of energy. So it makes common sense to actually have a unit which actually is a lot easier to use. So giving you normal numbers, okay, so an electron volt is what they're going to use. So you can see an electron volt quite clearly there. Learn all these are going to be definitions on your exam. 1 electron volt is the energy transferred when an electron travels through a potential difference or a voltage of 1 volt. Okay, so that's an electron volt. Now this is something which is much smaller, like we said, than a joule. And a very common number you need to remember is that 1 electron volt is 1.9, no it's not, 1.6 times 10 to the minus 19 joules. So that's a conversion you will have to do. Okay, so just to practice maybe converting a few of those things, it tells you how on the bottom of page 210. Have a go at the questions on page 210. Press pause. Hello. Right, okay, you can also see on page 210, okay, the equation which is energy or work done is charge multiplied by potential difference. You did that at GCSE, so E equals QV. You can actually change that. Instead of Q, write E for the electron charge, and V is still potential difference. But the energy gained, the work done on an electron in a magnetic field, okay, you can see it here. So E times V, that's the work done, or the energy gained by an electron, is going to be transferred all to its kinetic energy if there's no energy losses. Okay, so that's a way you can actually work out how fast an electron is actually going in a potential difference, and I can't quite make my camera work, but there you go. So that's how you can rearrange that equation to find out exactly how fast an electron goes in an electric field. Okay, so if you want to have a go at some questions on that, it's page 211. press pause. Okay, page 211 talks about an experiment you can use to give you a value for the Planck constant using light-emitting diodes with specific wavelengths and colours. And all of those you can actually end up by drawing the right sort of graph, y equals mx plus c, and from your gradient you can estimate the Planck constant. But have a little read of that if you want. And then if you do want to have a go at it yourself drawing the graph, what's a graph? Graph, then it's on page 212, question 9. If you want to have a go, get some graph paper and press pause. Okay, last thing then is the photoelectric effect, which was basically where people actually started to believe that light could really behave perhaps as a particle again, because after a while, after Newton came up with the ideas of it being a particle, it was completely replaced by Huygens' wave theory. So the idea that a particle could be what light is made up of was completely forgotten about until this photoelectric effect. Okay, so the idea is if you have got any form of electromagnetic radiation shining on something like a piece of zinc, okay, it turned out that if this was quite high frequency, then what you could do is actually any charge that was on here, you could discharge. So you can actually see the photoelectric effect. The idea that light can make electrons move away from a piece of metal, okay, is something which is called photoelectric effect. Okay, the idea that photons or light can make electrons be released. Okay, so the idea is, if you have a little look, there's another definition there about threshold frequency. Okay, so the threshold frequency is defined as the minimum frequency required to release electrons from the surface of a metal. Okay, so it's got to be from the surface, and those electrons are called photoelectrons. So that's the idea that it's just like ionization in a way, I suppose, that energy is needed to release electrons, okay? And the energy needed for a certain type of metal is called the work function, okay? That's the Greek letter phi, okay? So the idea is energy comes in and electrons get enough energy to move away. Now, if this was a wave phenomena, you would expect a higher intensity of that wave coming in would release more electrons. And if it was also a wave, you'd expect a higher frequency that has more energy would also release more electrons, okay? But what they actually found, and if you want to read about this on page 213, you can, that was the idea. So the energy that comes in goes into overcoming any attraction, okay? So that's called the work function. So the energy needed to release the electron. So whatever comes in is equal to the work function, the energy needed to release it, and then what's left over is the maximum kinetic energy of electrons. They might not have that much, but that's the limit to what they can have, okay? If one electron is released by one photon, okay? So that's the idea behind the photoelectric effect. This maximum kinetic energy can't be explained by the wave nature, okay? Because there should be unlimited kinetic energy, because any wave could, waves could combine and all that energy could go into one electron, and then it'll become a photoelectron. But the idea is it doesn't. One photon releases one electron, and that photon has a discrete particular amount of energy, and because of that, there's a maximum kinetic energy that can go on to the photoelectron. Okay, so that is the reason why people believe it has to be represented by photons. Okay, so if you have a little look, you can carry on reading about this in a lot more detail than I'll tell you right now. So page 214, it goes through all that, and if you want to have a go at some questions on that, then have a go now. Press pause. Okay, so page 215 is a little summary about wave model and photon model. What would happen if, in terms of the photoelectric effect? So that little table is a nice little summary talking about how the photon model can explain it, and that's why photons were pretty much assumed to explain the photoelectric effect, explaining that light could behave as waves and as particles, okay, which is what we call wave-particle duality. Okay, if you want to have another go at some questions, 12 and 13 on page 215, have a go now. Press pause. Okay, moving on, last little bit. So what is light then? That's the weird thing, okay? If light can behave like a wave, brilliant, okay, but it also can interact with matter and actually behave pretty much like a particle, like a photon. Now the interesting thing is, where is the line? What's the limit? Because photons are a strange particle, well, they're not a particle. Photons are a strange virtual interaction type particle. So the question is, well, where does this small, strange quantum effect end? Okay, quantum tends to describe very small things, but the question is how small does it become? How small does it need to be to still behave like that? Is there a limit to the size before it behaves macroscopically? That's big scale. Okay, and this guy, Louis de Broglie, or Louis de Broglie, as you'll probably call him, he came up with the idea that if electrons, they are particles, could they behave as a wave? Do they have an associated wavelength? So he proposed that the idea that the wave property of a solid particle that we would think of as quite an obvious particle could be linked by this equation. Okay, the wavelength is the Planck constant divided by the momentum, mass times velocity. So any particle that has mass and it's moving, okay, it's got momentum, and as a result of that, it will have an associated wavelength. Now, if you actually do a calculation for an electron, what you'll find out is that the size, the characteristic wavelength will be around about 10 to the minus 10 or 10 to the minus 11 meters. Now, that is around about the size of an atom. So if you can somehow make that interact with an atom, you might see diffraction, and that's exactly what happens, okay? You do get electron diffraction, so you can see there's a little picture there on the bottom of the page that is showing you electrons producing the sort of pattern you'd expect from diffraction. Okay, so electron diffraction does happen. You can make electrons, what we would perceive to be a definite particle, behave as a wave, which is a very bizarre phenomenon. But again, that backed up the idea that it could behave as both, this wave-particle duality. Okay, so the idea is this electron diffraction is something that could then further be investigated, and you can actually have a little look at wavelengths and whatever else. But if you have a little read through the rest of the chapter, it just goes into a little bit about the interesting nature of all this, if this is something you find interesting. So there's a few more questions you can have on page 218 if you like. Press pause. Okay, so in summary, page 219, just have a little read of that. Those basic facts, you just need to know them and learn them and be confident with them. So that rolls over onto page 220, where you'll find some actual exam questions. So again, now that you are finished, go to page 220. Okay, there's a lot of questions on there. Have a go at the questions, see how you do, check your answers. And once you've done that, again, if there's anything you're not sure about, bring a question to me in the lesson and I will go over it with you. Or if you're quite happy with all that, have a look at some past exam questions and just see the scope and the depth it goes into on this topic. Okay? Rock on. I'll see you in on.
Now I had the time of my life. No, I never felt like this.